So hello everybody, I'm Chen. Thank you for having me, and thank you, Kobe, for arranging this wonderful meetup. I'm going to talk about vulnerabilities through DNS, a little bit about me before I get into it. So my name is Chen. I'm a co-founder and chief architect of Enzo Security, an ASPM platform. I live in Tel Aviv. I really like to build things in computers, but also in the physical world. And I've been doing application security since 2004, from penetration testing to certifications to many different kinds of activities. I also spent a few years building applications myself, so I got to see what it means from the engineer perspective, and it's not so easy to build secure applications. And today I'm going to talk about some things that are related to DNS-related vulnerabilities. So in this talk, what I'm going to cover is a general discussion on why do we trust names so much? How come we establish such a huge trust in names? And then why should we discuss a little bit how should we do it? What can fail? What can bring additional risk when we're building on trust on DNS? What can be the possible impact when it fails, when something along this trust chain or trust layers fails? And then what can we do as practitioners, as people that practice application security and that try to help our teams or as developers, how do we deal with it? How do we approach this problem from mitigation perspective? So let's start with a little bit about why do we trust names so much? So on a fundamental level, the combination between the global DNS system, the domain name system, and the public key infrastructure is arguably the most mature and scalable trust system that we have on the planet, that the humankind has. It is battle tested, it has been through a lot, and it basically gives us what actually powers the internet as we know it today, and especially when we talk about web technologies, about things that runs inside your browser. It gives us a scalable trust infrastructure that is almost seamless to integrate with and to start operate inside as an entity, with getting a lot of out-of-the-box trust elements that you can build safe interactions between different platforms and different systems and different companies over the internet. A few core properties of this combination that enables this is the fact that the DNS itself, the domain name system, is decentralized on one hand, but still backed by governments. Governments has a huge incentive to make those systems safe, and sometimes it can happen also to the other side, that government has some control over these over segments of the DNS infrastructure, and they can affect it also in a not so positive way. But it is backed by government and decentralized, two properties that contributes into the solidity of this infrastructure. The PKI and the public key infrastructure is completely decentralized and also independent from government, which means that even when the government goes rogue and does things that they shouldn't with manipulating names in different ways, we still, as citizens, as users of the internet, we still have protection because of this decoupling between the authentication DNS. And I'm not talking about secure DNS protocols. I'm just talking about the basic DNS protocol and the system, more importantly, the system. This independent of authentication infrastructure let us give us the option to play with DNS in kind of a safe way, without knowing that if something breaks on the DNS level, we can still authenticate it with cryptography that is fully open, and everybody can read into the cryptography itself. Everybody can build the same cryptography. It's fully open, and these things together give us this kind of confidence that we can build on this trust system. Let's drill in to talk a little bit about how do we actually build the trust based on those two elements. So at the foundation, we have the domain name system itself and the public key infrastructure. And we have different methods or different mechanisms for authentication of different parties, building on those two building blocks. So we have domain validation, just direct domain validation to assess if names on a specific domain, and we can build different kind of authentication subsystems based on purely domain validation, basically asking who is the owner of this domain record, usually by making sure that the person who's trying to, for example, enroll PKI through, let's say, Secure, for example, can create a new record in this domain. And by that, we do domain validation, direct domain validation, and we can bootstrap another authentication subsystem on top of it and build another layer of trust. It's very common to do enrollment of PKI based on domain validation, but you can also enroll other assets. You can enroll a full infrastructure as a service, platform as a service, different kind of website platform, email platform, office services. Everything can be enrolled on top of this sort of domain validation. And on the other hand, when we talk about interactive interaction between your clients, most notably browser, we build on domain name resolving together with public key infrastructure for authenticating servers. So to make sure that servers are the kind of the entities that we think that they are when we get the resolution from the names. And based on this, we build the entire origin isolation security model that is incorporated and implemented in browsers and that we all use on a daily basis. Is we can build this layer on top of that, and on top of this we have many different applications of authentication, identity federation, resource sharing, different kind of things that we can do once we know who we're working with, whether it's another user or another vendor, another provider in the internet. We can build very complex and very rich resource sharing scenarios based on this trust system that starts from combination of DNS and public key infrastructure. But of course, this is never, no trust system is always is resilient to everything. And in fact, this has been challenged, this combination has been challenged in many different ways. And of course, it has many failure points, or many possible failure points. We can talk about root level failures, or failure on the authority level or at the system level. But there are also failure on any kind of implementation that along this among these layers or along this trust chain, if you may, which includes everything from not understanding exactly what the trust mean. So when we will get a validated record of some kind, missing understanding of what it actually means, can you actually build on top of it, but also some scenarios like what happens when the owner of a specific record changes. Let's talk a little bit about different cases. So we go from cases when it actually works properly, and with all the criticism that us as application security community can have on different implementations and different standards and different challenges that we have, for example, in cookies, when still after decades of using them, we're still very concerned and report different problems with cookies to a larger sense. These protocols, most notably the HTTPS protocol, is actually providing a lot of tools for building very solid trust and very collaborative work on the internet. Different origins, different businesses can collaborate based on it in a rather safe way. Of course, there are always problems, but in terms of the scale of it, in terms of the features that it allows in almost transparent fashion to builders to people to makers that build into the web environment, especially. And especially when you consider also the additional implementations, application that builds on this, like a different kind of identity federation protocols You, in a way, and of course this is somewhat a perspective, but in a way, this combination has proven itself to be very powerful and is allowing us to build a lot of trust, and that we can actually work with in the internet, in the open, and it's not such a simple thing. And in this sense, we have a lot of success with this trust system. However, the complexity of transforming layers of implementation of different protocols together to create this situation can fail in many different layers, can fail in many different points of the implementation. So we have what I call local or domestic failure of the parts that play part in using trust that is based on names. It can be anything from the actual mechanism used to validate signatures that is crucial for a solid PKI, up to the actual use of different origins inside browsing context and the implication that this can have on the actual final result, which is being able to isolate your application in a proper way and protect it from abusive cross-origin calls and resource sharing. And again, most of my talk here is from focus on web technologies, but when we talk about other kind of channels and other kind of protocols, it changes a little bit, although the main elements still play in the same way. We can go also into talk about epic failures, or places where the system almost failed completely and dramatically. And this is one of the cases is a 2011 breach of a CA, of a certificate authority. Let's drill in. So what happens when a CA is compromised? When a CA is compromised, we have a global impact of having of not being able to trust certificates anymore until the certificate until the infrastructure has revoked all the certificates that were issued by the CA, and that the operation systems has removed the trust on those specific authorities. We have a period where we are all at risk at being exposed to man-in-the-middle attacks, basically. But in order for this to really be impactful, we also need a breach of the DNS system. It can be very local, it can be global, it can be domestic, it could be national, but without breaching this system, a breach to CA is less impactful for all web technologies and for standard use of a CA backend. Of course, other trust chains might not be so well isolated when this happens, but even on a basic level, the fact that these are two infrastructure running together side by side and complementing each other is very useful in limiting the impact of a breach. So in the DigiNotar case itself, like I said before, 2011 case where someone, and of course about these cases, we always need to be very cautious because we know what we know, we don't know what we don't know, and to breach and to mount an attack of this scale requires a lot of thinking and a lot of preparation. So we don't really know who are the actual actors and what was the actual thing behind this. But what we do know is that a Dutch CA that was fully trusted by all the browsers, all the operation systems at 2011 was fully compromised. We know this because as part of the research, someone uncovered 500 fake certificates, including certificates to wildcard certificates for Gmail and these kind of certificates. We also have this report from anonymous user reporting about failure to connect to Google. Not so clear if we can trust this report as it is because it already has a spoiler to the actual hack. I'm not sure what is the meaning behind this, but But the bottom line is, and the pastebin of the certificate still exists. You can still access it today if you look. The bottom line is that someone did breach the system, did compromise CA, and did issue certificates that can break our can fully break our name validation routine, and have us talk to a third party once we think it's Google. It's actually not. Opening up everybody to man-in-the-middle attacks. But the thing about this attack is that it was, even though it was very scary, first of all, only the public key infrastructure was fully compromised, and for a short amount of time, and it was also possible for users to easily uncover it because of the fact that somewhat because of the fact that only that the DNS system was only locally or domestically compromised and not globally. But even more than this is because we have some different failover mechanisms that allows servers to allows people who operate in the internet to protect themselves even in these kind of cases. We have a peaking that is not recommended anymore because of the operational problem that it can cause, but we can still have extensions that will reduce the options to do SSL stripping, like HSTS, and other ways to make sure that we have some failovers to make sure that we detect and alert for these kind of scenarios. And this is why even in the most severe failure scenario, when the trust system, when the authority is compromised, we can still recover quite quickly and also discover this event quite quickly. Moving forward to, if the DNS system itself is compromised by itself, still the PKI part will authenticate the servers, and we are still not fully compromised. So like I said before, there is a lot of failover and ways to still be safe even when an element is compromised. When we go on and think about other reasons to fail, other places where we can fail, so even if the root certificate authority or the global DNS system is not compromised, we can still make mistakes. And those mistakes are one of the main problems that we see today with DNS management, is that we are managing records. Some of us manage a lot of records for many different purposes. The event of creating a new record is something that happens in a specific point in time and not necessarily is relevant for the future always, and we don't necessarily include it in our threat modeling, and we don't necessarily think of different scenarios that can result from having a bad DNS hygiene. And two main cases for this is that we manage dangling record, meaning records that points to things that are no longer what they were when we created those records, or we created those records to serve some resources and we backed off and didn't serve that resources, and it's still available in the internet. And a very classic case would be setting up an S3 bucket behind one of our names, but then doing only the name creation and not the S3 registration, and which results in what we call the S3-based subdomain takeover. This is one case. So general concept of records that were created for a purpose, but since then the target of the record, what the record points at, has changed or changed ownership, or that it was never even established and it points to somewhere, to an IP or to another record that is not owned by us, and someone can operate behind this record and be part of our domain. Another case that is very similar to this in its impact is that the records are managed by us and are pointing to wherever we want them to point to, but those places like a third-party application or web application that is operating in our origin is vulnerable to client-side attack vectors. or to some client-side attack vectors. And then every vulnerability that they have becomes your vulnerability with some limitations, of course. So bad records are very similar to compromise domain name system. It depends a little bit on how do you do SSL termination. Sometimes it's a more complex scenario when you actually do the SSL termination and based on DNS you forward a request. So the PKI would not protect you in those scenarios. But if you didn't do that in a normal scenario, it will be the same as having bad DNS system, an untrustworthy DNS system, and someone can potentially do part of those things based on that broken record or record that is not managed properly, or even a full namespace, a full domain that is not managed properly, and follow up with different domain validation scenarios that can breach some authentication, identity federation, resource sharing facilities or subsystems that you have. If we talk about failure anywhere along the trust chain, so it can be really much anything that results in breaking isolation. Again, focused a little bit on a web realm. So even if you do iframe implementation, you don't properly check the way that the iframes are checking origins before and after, and when they receive messages from other frames, you would have the same kind of results. You will have breached origin isolation. The same goes for if you're not controlling cross-site requests, if you configured your course in a proper way, and even if and when we talk about other mechanisms that operates inside, even things like a broken cryptographic element inside the PKI that is used in PKI can cause the same thing. Although that if I already put MD5 here in the slide, so we have to mention that when MD5 was when researchers started to report that they have means to breach MD5. By the time that it became practical, the PKI was already eradicated the use of MD5, and the same goes for RC4. So we can see that these are not so dangerous, but as the application security folks, we all know how common are things that breaks our isolation and expose us to client-side attack vector. And we just now have to add another item to that list, and that item is having bad DNS hygiene. And with subdomain takeover or dangling domain records or dangling IP records, you can have the same kind of results of breached origin isolation and having someone else interacting with your origins in an uncontrolled fashion. The most common impact of such a scenario would be that the origin is not isolated properly anymore. And that now it's very similar to cross-site scripting, to course misconfiguration. You have a problem in protecting your origins from other internet origins, and meaning that another origin can either script your website or interact with it, consume and create resources in it. But of course, there are always other things like much more serious scenarios where a full subsystem is compromised. This can happen, for example, when the breach origin isolation is in your authentication segments of your application, but also in other subsystems like, for example, email validation. Let's drill in a little bit to what is the meaning behind breached origin isolation. So breached origin isolation, I'm pointing out 3 different cases of it that can lead to it. So a subdomain takeover, it's a record pointing to an unclaimed cloud resource. It doesn't have to be a cloud resource, but it's usually a cloud resource like an S3 bucket. And you already, so in your development flow, you created a record that points to that bucket, but you never claimed the bucket, or you've claimed and you closed it. And what happens now is that there is a bucket. Everybody with an AWS account, which means everybody can claim it. And it doesn't have to be S3 bucket. It can be equivalent technology in any cloud provider. And other things like even a Wix site, Shopify, different kind of cloud resources can be relevant in here, and the attack in this case, or the weakness, vulnerability in this case, is that someone can create the record that claim the resource, establish the resource. Your record is already pointing at it, and all I need to do as an attacker is to deploy my my cross-site scripting framework there and start interacting, operating inside your subdomain. A Dangling Ip Record is a similar case, but in this case, you're just pointing to an IP, but this IP is no longer yours. It has been claimed, it has been released from your resources. Someone else is operating on this IP address. And another case is that there is no problem in your DNS management as it is, but you have invited someone else into your origin, someone else plays inside in your domain, in a subdomain, and they have client-side attack vector vulnerabilities. So someone can mount a client-side attack on their application. And because they operate inside your origin, inside your subdomain, the impact is mainly on you and not necessarily so much on them. Possibly also on them, but mainly on you because you brought someone else into your origin. Let's drill in to discuss in more details. So malicious script. So one case is a breach to origin isolation that allows malicious script in subdomain. It can be from Dangling record pointing to any web server controlled by an attacker. It could be a Dangling IP record. It can be a CNAME, and once it points into any server or bucket or basically a mobile client, a web client created by the attacker, they can run scripts in a subdomain. The same goes for cross-site scripting kind of attacks on third party in your domain. And the impact is somewhat limited when we talk about origin isolation because of the way that origin isolation, cross-domain resource sharing, and in general, the browser security model is. When you operate in a subdomain, you have some limitations. You can still, it really much depends on how transparent authentication materials or cookies has been created by the main origin, by the domain itself. If they are not properly isolated, and if the system on the other side was built to give a lot of trust to applications running in subdomain, you are still very much exposed and can be attacked in this way. Another case of breach over origin of isolation is that a malicious script is running on a trusted origin. It's not exactly running on your subdomain, it's just running on an origin that you trust. So you already implemented the course protocol with a specification to allow someone to say, submit authenticated request from a subdomain, from a origin, and then this origin was taken over due to DNS related attacks. This is another case where we can suffer from breached origin isolation. But of course, there are always some more serious things like a full failure of a authentication subsystem. So think of a very basic case where the full namespace is compromised, or someone created a trust in ChenGourArie.com. I owned this domain for a while and I registered it and I used it for some things. People made some trust on it, but then I didn't renew it and someone else can take it. And I think that maybe the good folks from JFrog Security will mention it because they just recently published an article about how this was reflected in package management related problems. So someone used these kind of flows also to take over some packages. How do we approach this in terms of mitigation? How can we avoid this? How can we solve this? So the main approach to solving this is the main thing to consider when you want to tackle this issue is that it has to be done systematically. It's not something that you can, okay, you wake up one Monday morning and say, oh, I'm going to check if I have this problem. You did it today, tomorrow it can change completely. The resources that you're pointing to can change, your records can change, and it's something that has to happen systematically and continuously. And this is why you have to run through a process, a continuous process of asset inventory, that you have to know your domains, you have to understand how you're using names and what could be, where is your weak points in terms of origin isolation. And when you build applications and you build on the option to trust other origins and to collaborate with other systems, you need to consider and bring in this question into your flow and ask the right questions when you work on the implementation to make sure that you're building in a secure way to do use sharing of resources in the internet. Let's drill into inventorying web assets a little bit. So you need to track all the records managed in the domain. So have a full list of all the records, understand all the records, even those that are not mounting any applications behind them, just so you will have the clarity of what records you have. There are some nice tools to find records, but the way that we do it at Enzo is that we integrate with your own management systems, for example, Route 53, and we pull this information and we manage this inventory for you. And then we can follow up with some tests, like for example, a test that is done by these open source tools. Subfinder and Project Discovery in general is very useful for doing this with open data. Subfinders will help you to find your existing domain records. You need to find records, to find IP records and CNAME records, and eliminate Dangling records, shadow and SSL termination when you're doing it for sources that you don't want to, and consider claiming the referred resources. So those S3 buckets that are pointed by those records, claim them so no one else could. Then you need to follow up with doing the same things, but then find servers, web hosts, servers that host web applications. And then you need to also inventory and assess if they are running some sort of origin, of course, resource sharing protocols, if they support course and they allow other origins to interact them, and you need to include those origins in your inventory as well. I will finish up very soon because my time is up. So let's drill into a little bit protecting origin isolation. You need to extend your threat model to ask wherever it's relevant, wherever you're having some sort of trust in origin, and surprisingly enough, mail validation includes this, but other scenarios as well. But ask what happens when the record, the owner of the other side changes, the IP, the resource. What happens when the owner changes, and then build threat models based on this question. You need to always pay attention to core settings and include also server-side checks as part of this implementation. Try to be as explicit as possible with cookies. I know that we've all been complaining about cookies for a very long time, but it doesn't mean that we can stop maintaining the security of cookies. Do onboard to extensions like HSTS. And if you can afford, if you can do it, do use extension like a content security policy. It will greatly improve your ability to control what kind of content is running in your origins. In conclusion, we have DNS can affect our origin isolation, can bring us more vulnerabilities. We need to systematically inventory all our relevant assets and lead the process to build layered origin isolation. Which also including an important part is extending your view and extending your threat perception to also include this threat under your scope. Few words about Enzo and then I'm done. So Enzo is an application security posture management solution. It's a platform that lets that with a lot of integrations to data that you already have and to activities that you already conduct, brings a lot of information about your application asset inventory, and with our very nice portal let you manage all the activities and all the processes to lead a very strong and systematic application security program that can scale as your company scale. Also check out the Apsec Map. a community-driven project to share information about different vendors in application security that is intended to help everybody out there find the security solution that they need. And this is built based on external submission. So if you are a vendor or if you find any tool missing in the map, please share. And we will include it in the map. That's it for my side. Thank you very much for listening.